Welcome. Thanks for coming and listening to this talk, either for the Educational Data Mining Conference or wherever you happen to be located in time and space right now. My name is Stefan Slater, and today I'll be presenting on some work that I've developed with my colleagues Dr. Ryan Baker at the Penn Center for Learning Analytics and Wang at the University of Wisconsin-Madison. We've developed a method for improving model performance with a process that we call iterative feature engineering. So, getting predictive models to perform better is one of the core questions in data science. A model that fails to accurately predict its constructs of interest is of no use. It's functionally a coin flipper or a dice roller. Considerable time and energy goes into the improvement of model performance, and there's no shortage of scholarly work on this topic. Your basic data science pipeline often looks something like this. Once you've collected and prepared your data, you engage in the practice of feature engineering, or occasionally knowledge engineering, the process of extracting and constructing meaningful and relevant features from transactional log data. Often this process is cyclical, with multiple iterations of modeling informing the development of additional features to boost performance. Once some threshold of performance is reached, the model is then used to generate predictions, which are either put into production or used in further steps of modeling and development, such as in model ensembling. Feature engineering has been identified by researchers as a crucial component in the overall process of constructing models, and as learning systems grow more complicated and more sophisticated, as they afford students with more diverse pathways to demonstrate learning and display mastery, the feature engineering process grows more and more challenging. What features are meaningful and relevant? Which behavioral patterns matter, and which don't? Some approaches that have been used include the use of content experts, who have a greater degree of knowledge regarding the system and its processes, and its learners, or the use of qualitative coding to identify important behaviors. However, the increased scale of data collection can make hand coding a difficult, expensive, and time-consuming process. What we're proposing that we do with iterative feature engineering is that we cheat a little bit. We go all the way to case prediction, and we look at the cases where the model fails to predict its construct correctly. When we return to our feature engineering step, we focus on these cases of predictive errors specifically, generating new contextual features based on cases the existing model wasn't able to correctly handle, and in that process, hopefully providing the model with more information to generate accurate predictions in the future. By focusing our feature engineering efforts only on cases where the model fails to correctly predict, we can reduce the amount of time needed to employ feature engineering approaches like expert coding or qualitative analysis. But before we get to the details on that, let's talk about the context of this study and where our data came from. We used data collected from an empirical study conducted within Physics Playground in the spring of last year. Physics Playground is a physics simulation game developed by Dr. Valerie Schutz's lab at Florida State University. In Physics Playground, students solve various physics puzzles by constructing simple machines such as levers, pendulums, ramps, and springboards. These simple machines are used to move a green ball towards a red balloon elsewhere in the level. Physics Playground's levels employ multiple underlying physics constructs such as conservation of momentum, the transfer of energy, and properties of torque, and offers support and scaffolding in the form of worked examples and physics animations if students become stuck while playing the game. For our work, we chose to model student quitting behavior in Physics Playground. We believe that quitting is an important construct to study, as it may be related to student affect, persistence, and time on task. Additionally, quitting has previously been modeled in the Physics Playground literature, and this gave us a good point of comparison for the development of our own models and feature reengineering methods. We operationalized quitting as follows. A student was considered to have quit if they spent at least 5 seconds on a level, and they left the level without successfully completing it, and they went to play another level in the game. Condition A keeps us from categorizing students accidentally clicking on a level and then leaving it as a quit. Condition B defines a quit as being explicitly not a successful attempt. And Condition C prevents us from calling ends of sessions quit events, such as when a student stops playing for the day. Once we had developed this definition, we took any student action that happened within 120 seconds of a quit event, and we labeled this as quitting. We did this because we wanted to model the lead up to the quit event itself, as simply predicting the moment of quitting may not leave the system, or a teacher, enough time to intervene and provide a student with additional scaffolding and support to keep them working productively. We started by fitting a baseline model of quitting to the data, using features that had been previously identified in the literature. This model consisted of 32 features, and was fit to the data using logistic regression, in order to generate a % likelihood that a student will quit within the next 120 seconds, given their actions in the game so far. This model performed reasonably well, with an AUC of 0.688. This performance is slightly worse than previous attempts at modeling quitting in Physics Playground. However, we were limited in the modeling techniques that we could use for this work. The eventual goal of this project is for a quit prediction model to run live in Physics Playground as students play the game, and the Unity architecture that the game is built on, combined with the frequency with which the model is updated and calculated, meant that we had to use relatively simple algorithms, such as linear regression, for this project. Once we generated this initial model, we generated a confusion matrix of model predictions using a cutoff of p equals 0.5 for the logistic regression model's predictions. This confusion matrix allows us to visualize where our instances of type 1 and type 2 error are. And these instances of model misprediction are the instances where we can improve model performance by generating additional features for the model to use. These cells, the false positive cell and the false negative cell, are the instances that we want to focus on for our feature reengineering procedure. We applied these predictions back onto the data, and we generated two subsets from that. One for instances of type 1 error, and one for instances of type 2 error. If any student action for a given attempt contained a prediction error, we considered the entire attempt to be an instance of that error. We used text replays as our method of reengineering features for type 1 and type 2 error. Text replays, described by Baker, Corbett, and Wagner, are a process used to quickly label log files with student behaviors of interest by using human coders to manually label pretty printed student log data. For this work, we used text replays as a way to identify trends and patterns across multiple Physics Playground players and utilize these trends in generating additional features that describe previously unknown player behaviors that may describe quitting. In order to limit potential overfitting, which we'll describe later on, we only conducted this process on cases of model misprediction, and did not cross-reference the frequency of these patterns against true positive or true negative cases in the model. So in this log data here, you can see student 168C2 in the level downhill. They initialize the level here. They draw a couple game objects. This identified verb here means that they drew a simple machine that the game was able to identify, something like a ramp or a springboard. And then later on down here, they pass the game level, they press the next button, they receive their achievement for the level and their silver badge, before moving on to the next game level, scale. Our text replay process identified 13 behavioral features that we believed could be of relevance to students' decisions to quit from an attempt. Some of these do what they say on the box, like previous attempt duration, but I do want to explain a few of them. In Physics Playground, if you click on a ball, it moves slightly. You can use this to get your position just right, or to move your ball up shallow inclines. And these events are recorded as nudges. So consecutive nudges is a count of how many times players nudged a ball in a row without recording any other action, such as drawing an object. Net objects drawn is a descriptor of how many objects are on the screen at once. It's the number of objects that a student has drawn so far in an attempt, minus the number of objects that they have erased or deleted in that attempt. And for unusual object used, each level in Physics Playground has one or two underlying knowledge components, or KCs. And these KCs correspond to the simple machines that should be used to solve the level, in order to correctly apply the physics principles that the level is meant to illustrate. So if a student draws a machine that's not used to solve the level using the appropriate KC, such as if a student draws a pendulum on a level that is supposed to use a ramp, we call that an unusual object use. And so these are our results. On the left, we plotted three models. The original model is in blue, with an AUC of 0.688. This is our model that used previously identified features from the literature. The enhanced model, with our iteratively generated features, is in yellow, with an AUC of 0.812. And the quit flush model, which we'll get to in a minute, has an AUC of 0.616. The addition of our iteratively engineered features improved model AUC by nearly 20%, which is a pretty large improvement. And on the right are the two features that contributed to this increased performance of the enhanced model. the consecutive nudges feature, which we described earlier, and early scaffold use, cases where the student uses a learning scaffold less than a third of the way into a new attempt. The AUC in parentheses for both of these features is the AUC of the enhanced model if this feature was held out. In other words, it's the performance gain that this feature is responsible for in the overall model. The rest of the features that we developed, when held out from the enhanced model, had a negligible effect on the model's performance. The difference in AUC between the original and enhanced model is driven almost entirely by just two of the features that we developed. As for this quit flush model, one of the things that we noticed during our text replays was that nearly all of the cases of type 1 error, the model predicting that a student will quit when the student does not quit, shared a lot of similarities. Specifically, these cases were almost all attempts where the model initially began by predicting that a student would quit, but then stopped midway through the attempt. We hypothesized that these instances might be left over from when students actually quit. Perhaps the model successfully predicted these, and moved to a new level and began working productively again. In other words, the model's prediction of quitting lagged a bit behind when students actually quit. To give the model a chance to improve in these cases, we took every instance where a student quit from an attempt, and we zeroed out every feature in the model at these points. Subsequent attempts would then be starting with no information on previous student actions. Previously, the model would continue increasing its counts across an entire session, regardless of how often a student did or did not quit. And as you can see from the graph, this approach didn't really work. Our quit flush model performed even worse than the baseline model that we started with. So this suggests, at least to me, that a couple of things might be going on. First, quitting might be more of a student-level variable rather than an action-level variable. Maybe some students are more or less likely to quit, suggesting that a model of player typologies may be useful in improving model performance further. Or maybe the attempt-level grain size that we use for our iterative feature engineering process is too small, and contextual information from preceding and following attempts is important for fully understanding quitting as a construct. This is one of the things that we're hoping to explore in further work on this topic. When we were devising this method, one of our primary concerns was the potential for overfitting. In this work, we iterated on our features once, but we didn't need to stop there. We could have iterated again and again until our model reached perfect prediction, endless monkeys banging on typewriters to get our threshold set just right. Obviously, this isn't a desirable goal, as the resulting model would fail to predict anything meaningful on subsequent datasets. But engineering and re-engineering features specifically on cases of incorrect model predictions does enable the possibility of overfitting to the particulars of the dataset. In the time between submitting this paper and this presentation, we tried applying these models to a new dataset of physics playground data that was collected this spring. Unfortunately, the context and protocol of that study, as well as updates made to the game itself, prevented either of our models from performing very well on this new data. Both the baseline model and the enhanced model returned AUC scores of around 0.6, a significant performance loss. And we're not really able to tell whether this is due to overfitting on the first dataset, or whether the new dataset is just too different from previous versions of the game for any of our models to work that well at all. Nonetheless, we hope to more fully explore the issue of overfitting with this technique once we have appropriate data with which we can answer that question. And finally, one of the applications that we're excited about for this method is in developing models that are better able to address uneven prediction quality and heterogeneous data. Instead of looking at incorrect predictions across the entire dataset, we could also have looked at incorrect predictions for specific demographic or other grouping variables of interest. For instance, we might be interested in boosting performance specifically for women or for high school students. We could do this by looking at incorrect prediction that the model makes for that specific subgroup, and then using iterative feature engineering to build new features on text replays of that subgroup playing the game specifically. A lot of previous literature is focused on demographic differences in model performance, and in keeping with the theme of the conference this year, we think that this method of iterative feature engineering is a promising pathway towards engineering better features and better models for datasets consisting of learners across multiple backgrounds and demographics. If you have any questions about this presentation, whether you were at EDM 2020 or not, you can reach me at the following locations. My email is slater.research@gmail.com. You can find me on Twitter at DataRefinery, And I'm on ResearchGate as Stefan_Slater2. Thanks so much.